So hello, everybody. I'm Dr. Abbie. I'm joining you from Michigan in the US right now. And I'm going to tell you a bit about how we can see black holes. I'm currently a research fellow at Michigan State. I also do some work at University of Michigan. My research is funded by the US National Science Foundation, and I use a telescope on the International Space Station. It's up there right now, and its name is Nustar. I'll show you a video of Nustar later on in the talk. So, if we want to talk about how we see black holes, we first have to talk about what is a black hole. Simon covered this a little bit in that synopsis that he read, but a black hole, we're talking about astronomical black holes here. So this is stuff that's up in space. In principle, anything could be a black hole if you could make it small enough for its given weight or its given mass, but we're talking about stuff that's up in space. So when we are thinking about black holes, you'll often see scientists draw what we call space, or the fabric of space and time. You'll often see us draw it like a grid. And anything that has mass, it has a gravitational force for it. And when it has this mass and gravitational force, it deforms this fabric of space and time. So our sun has a mass, and its gravity is what keeps the Earth in orbit around it. And so as we see right here, it is deforming this two-dimensional fabric just a little bit. A neutron star is a dead star that happens when a star is big enough to explode in a supernova, but not quite big enough to form a black hole. And so you get this thing that's about the size of just a city, but it's got like 1.5 times the mass of the sun crammed inside. They're really cool. We'll talk about them some other time. And these have even stronger gravity, so they deform it even more. So it kind of falls down into this hole deeper. And then a black hole is the most extreme form of gravity. And so it significantly deforms this. And so a black hole effectively is when you have a whole lot of stuff or mass in a very, very small space. And the size of the black hole depends on how massive it is. So the more massive the black holes are physically a lot larger. And by having all of this mass and being very compact, it's not just the mass, it's how compact it is as well. This gives it very, very powerful gravity. So one of the ways that we can study, or rather measure, the gravity of something is to talk about how fast you have to go to escape its gravity. So we call this the escape velocity, how fast you have to go to get away. So everything that has mass has an escape velocity. So the Earth, for example, has an escape velocity. Now, airplanes, these do not go faster than the escape velocity of the Earth. So airplanes can never leave and go off into space. They are always going to come back down. But rocket ships, these do go faster than the escape velocity of the Earth, which is how they can leave the Earth and go to the moon or Mars or carry satellites somewhere else in the solar system. And when we talk about how when things have stronger and stronger gravity, their escape velocity gets higher and higher. So you'd have to go even faster and even faster to escape away from them. And black holes get their name because their escape velocity is faster than the speed of light. Now, the speed of light is a cosmic speed limit. Nothing in the universe can go faster than the speed of light. So if not even light can escape from inside of it, then that means it looks black or dark to us. And so this is how they get their name, black hole. The parts of the black hole, kind of a diagram schematic. This is a simulation video done by one of my colleagues at NASA. And one of the two parts of the black hole that everybody has heard about, if you've heard of black holes before, is something called the event horizon. The event horizon is this point of no return. It's the threshold. Outside of the event horizon, it's possible for stuff to escape, but inside of the event horizon, that's where it's dark or black. That's where not even light can escape. And so we can't see anything and nothing can get out. So that's that dark part right here in the middle. But there's a part inside of that called the singularity. And the singularity, we think of it like a physical thing, but it's really more like a mathematical thing. We understand it much better with math than we do with physics or astronomy. And the singularity is at the center of the black hole. And this is where everything that is inside of the black hole is squishing and condensing and just the most incredibly dense thing that anybody can imagine. So this singularity is also a term that comes up sometimes in popular media. Also, alongside black holes that we can see in this video that you're looking at, we have the accretion disk, which is all this stuff swirling around the outside. We'll come back to the accretion disk in a minute. And then we also have this little photon sphere right around the outside here. So this little kind of shell of light of like kind of the last gasps of light that's just barely able to escape the black hole. Also not pictured here, but very relevant, are these relativistic jets. These are like fire hoses that are supported by magnetic fields, and they're shooting particles at a very big fraction of the speed of light. So not faster than it, but maybe at like 20 or 30% the speed of light. And so this is very energetic, and these shoot out from the top and the bottom of the black hole. So these are kind of the parts of a black hole altogether. You're going to hear a lot more about these relativistic jets with Dr. Greg Sivikoff next month. And actually, he and I work together on some of the proposals that he's going to be talking about. So you're in for a real treat next month. And one thing I want to convey here is that the danger zone for black holes, people get scared of black holes, but the danger zone of getting stuck and trapped is very, very small. Everything outside of the event horizon is possible for it to escape. It's only inside that you get stuck, and only inside of, and it's only with inside there, it's like, tens of miles, maybe hundreds of miles. It's very, very small. So this isn't anything we have to worry about. It's something that's just super cool that we can look at from afar. So there's two types of black holes that exist in the universe. We have small black holes that are formed from the death and collapse of a big star. So we call these stellar or stellar mass black holes. There are also big black holes that have been around since very early in the universe, and these are at the centers of galaxies. We call these supermassive black holes. You can tell we're very imaginative. The ones from stars are stellar. The really big ones are supermassive. And there is no limit on how big they can get. There is a lower limit on how small they can be. 3 is about the smallest, 3 times the mass of the sun is about as small as they can be, but there's no limit on how big they can get. So when I give you a number for how massive these things are, we're going to have a quick interlude about numbers. And this seems really simple, but bear with me for just a minute, okay? So the universe is really big, and so the numbers that we use to describe it get really big. But there's this kind of order of magnitude, or this scale between the numbers that's really, really difficult for us to actually intuitively grasp. So I have a little example to kind of explain this. So we all know how much 1 second is, right? So if you think about 1,000 seconds, this is about 16 minutes. So this time is going to pass with us here this evening. So 1,000 of something, maybe 1,000 seconds, is equivalent to 16 minutes. Now, if we think about 1,000,000 seconds, this is 11 days. So that's also a lot more time. But that's still, a week and a half. That's reasonable. That's something we can understand. So by going from 1,000 of something to 1,000,000 of something is like going from 16 minutes to a week and a half. However, when we talk about 1 billion seconds, this is 32 years. So for scale, I have only recently been alive for 1 billion seconds. This is a very long time. So going from 1,000,000 of something to 1 billion of something is like going from a week and a half to 32 years. This is huge. So even though it just looks like the M and the B are changing, there's a massive scale difference in the numbers of millions and billions. Okay? So when we talk about the smallest black hole we've ever seen, this is 3 times the mass of our sun. It's in the constellation Monoceros, so it's sometimes called the unicorn. And the biggest black hole that we've ever seen is about 60 billion times the mass of our sun. That's billion with a B. And there's probably a bigger black hole out there. We just haven't seen it yet. This is the biggest one that we've seen. And what's really interesting also is that we've got these small ones and these big ones, but there are effectively no intermediate mass black holes that are in the middle. This would be kind of like if you went to an alien planet and you saw a ton of kids and a whole bunch of adults and like 2 teenagers. You wouldn't necessarily think that the kids grow up eventually to become the adults. So we don't have any teenage black holes effectively. There's maybe 2 of them, depending on who you ask. And so this is a really interesting concept in astronomy of figuring out, do the small black holes eventually become the big black holes, or are they just formed totally differently? Is it just like, having like different aliens that you're looking at as opposed to having kid aliens and adult aliens? There aren't aliens here, by the way. I maybe shouldn't have said that. But how do we study them? So we've got these black holes. There's a whole bunch of them. They have different masses. How do we study them? Well, in most of science, you would grab one, put it on a table, shine a light on it, and study it. You can do this with many other fields of science, but we can't do this with astronomy. You can do it with some planetary science even. They've brought moon rocks back, for example. But we humans have never, ever been to a black hole. We've never been close to a black hole, and we're never going to because they're so far away, which is honestly pretty good. We can sit back from a safe distance and enjoy them. But we cannot just grab one, put it on a table, shine a light on it, and study it. Instead, in order to see one, we have to wait for one to send light in our direction. So a lot of astronomy is waiting. There's enough black holes that we can generally see a few per year, but we have to wait. There's a lot of patience involved and something called serendipity or luck, happening to look in the right part of the sky at the right time with the right telescope. So effectively, we see black holes by looking at the effects they have on their space environment. We're going to talk about all of those things now. So the first way we have of seeing black holes is by directly taking a picture with radio light. So this picture came out in 2018, and it was on the cover of many major newspapers. It was on the cover of magazines. It was all over the internet. And some people thought, well, this is just a lumpy orange donut. Why is everybody talking about this? But this is the most exciting lumpy orange donut I have ever seen in my entire life, because this is a direct picture of a black hole. So this is of the light that is right outside of the black hole. So this is stuff and light right outside of the black hole near that photon sphere area. And right inside of that dark part there is the black hole itself. This black hole is called M87 Star. It's a supermassive black hole that's at the center of a nearby galaxy. We tried also taking one of our own galactic center, of our own big black hole, but there was so much stuff in the way because we are in this plane and there's a whole bunch of like stars and gas and stuff between us and the center of our galaxy that it was actually kind of hard to take a picture of that. There was so much stuff in the way. So if we look outside and to a different galaxy, we can see it quite clearly, which is nice. So when we took this picture with radio light, though, it's not like we were able to just use a camera. So radio telescopes are these giant satellite dish looking things. They are many meters big, and oftentimes we use more than one of them to look at something. So this is an example of an array of radio telescope dishes, and they're all looking at roughly the same thing and combining their data together with computers. And in order to take this image of M87, this picture of a black hole, we had to use radio telescopes across the whole world so that we could make effectively an Earth-sized telescope. With radio telescopes, when you combine your different radio telescope, your individual dishes, it's like you have a radio telescope that is the size of the distance between them. So in order to take this picture of this black hole, we had to effectively make a radio telescope the size of the whole Earth. And the imaging power that they had for this is like if you were in New York City and you were able to look at the writing on a coin in Los Angeles. It's that much imaging power we had to use to see this black hole. And this is one of the biggest, closest black holes we had to look at. So this was extraordinary, both from a technological perspective and a scientific perspective. So when we keep adding more and more and more radio antennae to this, the more we add, the clearer and clearer the picture gets. So when you only have a couple, it gets very noisy, but the clearer and clearer it gets, you can actually make out these individual point sources in your image. This is a different example. This isn't of the black hole. So the more and more antennas you add of these radio dishes across the whole Earth, the more we can combine them in computers afterwards to get a clear picture of this black hole. And so here's a computer simulation that they use to compare to show what it might look like if we had even higher resolution images. Now, we're probably never going to get higher resolution images unless we can put a radio dish on the moon. That would be awesome. Then we'd have a radio telescope the size of the Earth-Moon distance, which is big. But otherwise, we are able to use these computer simulations and then apply a correction to it for what it looks like in nature so that we can compare our computer simulations with what we actually see to check if we understand what's going on. And only in the last maybe 2 years or so they released this new image where it's still this lumpy orange donut of a black hole, but there's these lines on it. And these individual lines here, this is showing what's called the polarization of the light. So polarization is something light has in addition to like color and intensity. And so if you have polarized sunglasses, this is something that is using the polarization of the light to either block or allow sunlight. So we kind of used polarized sunglasses to look at this with the radio telescopes to look at this black hole. So we added these lines. It's very exciting. It tells us about the magnetic fields. These are very important and very hard to understand. So this is one of the ways we have of seeing black holes. Another way we have of seeing black holes, and this is the way that I use in my own research, is when they are eating their star friend. Scientists call these X-ray binaries. So this is where we have a stellar small black hole and a normal star like our sun, and they're friends and they're orbiting around with each other. But the black hole is a bad friend, and it is slowly draining and eating the normal star. And so the outer part of the normal star is more gravitationally attracted to the black hole than it is to its own star. So it falls towards the black hole, and it forms this pancakey bit here called an accretion disk. And so this is fairly thin, and it goes around kind of the center, almost like a tutu around the black hole. And this accretion disk gets really, really hot because it's full of star stuff swirling around together. So first, I want you to imagine you can do this. Rub your hands together and feel the heat that you get from that. And if you do it more and more, the more friction you add to it, the hotter it gets. But don't hurt yourself. So the more friction we can add to something, the hotter and hotter it can get. And everything that shines heat, or that has heat, shines what we call heat light. So the human body is hot. We shine our heat light in infrared light. The sun is hotter than us. It shines its heat light in X-ray. And this accretion disk is so hot, it is 20 million degrees Fahrenheit. I should have figured this out in Celsius for you all in Canada. Sorry about that. It's still very, very hot. This is about 100 times hotter than the surface of the sun. And this is so hot that it shines its heat light in X-rays. We have a computer simulation here, and it's of a black hole eating a star. This is very sped up. Sometimes if it's a bigger black hole, it can gobble up the star in a matter of months, but usually this period is very, very slow, and it takes many millions of years for the black hole to slowly drain the star. And what I want you to notice as this comes around again is that the black hole is always there in the video, but you can only see it when it's eating the star. So the black hole's always there in the bottom left, but only when it begins to take the stuff off the star and eat it can we actually see it. And it forms this nice big accretion disk, and then we power these big jets coming out the top and bottom. It's very exciting, it's very energetic, and this is the kind of stuff I look at with my research. So the very first black hole that we saw, it's called Cygnus X1 because we saw it in the Cygnus constellation, and it is the first X-ray source we saw there. We saw this in 1972. So this is relatively recently in terms of the history of astronomy and looking up at the night sky. 1972 is very recent. And when we talk about X-ray telescopes, we're going to think about this in just a little bit more detail. One thing to keep in mind is that all of the colors that we see are a very small part of all of the types of light that exist. So we have this rainbow that we're used to seeing, but this is just a very, very small part of what scientists call the electromagnetic spectrum. So all of these types of light they're all different energies of light. Radio, microwave, infrared, visible, like what we're using right now, ultraviolet or UV, X-ray, and gamma ray. These are all different energies of light. And something that's really important with astronomy is when we're looking up at the night sky, we can use all these different wavelengths to look at stuff. So I already told you about radio light that we use to look at this black hole from a different galaxy. But not all of this light can actually get through the Earth's atmosphere. So radio light gets through Earth's atmosphere. We can see, if we have something on the ground, we can see radio light coming in from space. Visible light gets through Earth's atmosphere because we can see the sun. Microwave light does not come in. Our atmosphere blocks that. And ultraviolet light, a little bit of it gets through. That's why we have to wear sunscreen, because UVA and UVB do get through a little bit. X-rays and gamma rays, though, do not get through the Earth's atmosphere. And this is really great for the evolution of multicellular life on the surface, but it's a very sad thing for X-ray astronomers. So in order for us to look at X-rays from space, we have to put X-ray telescopes on satellites and launch them into space on rockets. This is very fun, but kind of expensive. So one of the X-ray telescopes I use is called Nustar, and it is on the International Space Station right now. It was launched in 2017, and it is this white box here in the middle moving around. We've got a solar panel of the telescope in the background. This is sped up about 100 times. And you can see it slowly moving as it's following its target as it moves across the night sky. So we are on the space side of the space station, not the Earth-facing side of the space station. And Nustar is about 1 cubic meter. So it's 1 meter by 1 meter by 1 meter. So it's like the size of a dishwasher or a big oven range. But it's a really cool one that can see X-rays coming from black holes and neutron stars. So I use Nustar regularly in my research to look at X-rays coming from black holes eating stars. There's another telescope that I use. It's called Nustar. This one was launched in, I think, 2012. And Nustar is special in that it can focus X-ray light onto a special detector in order to take clearer pictures. And so it has this really big metal structure to hold its two pieces together. And this is 10 meters or about 30 feet long. So this is very, very long. They had to extend it once it was up in space. And Nustar uses this to help focus the X-ray light because it's so energetic down onto the detectors at the back. So these are the two X-ray telescopes that I use to look at black holes eating stars. But there's a bunch of other ones you might have heard of, like Chandra or XMM Newton or AstroSat or HXMT. There's quite a few different X-ray telescopes that we use in space right now. Another way we have of seeing black holes is when we have massive, supermassive black holes that are eating other gas. So they're not just eating individual stars, but they're eating clouds of gas. And we call these types AGN and quasars. So the Chandra X-ray telescope is really good at looking at this. So this image I'm going to show is called astrosonification. So I'm going to move my microphone so that you can hear this. There are links in the slides that you'll be able to see later to actually go back and watch this for yourself. But as the beam sweeps up through the image, it's going to play a note for the different colors of the different intensities of the massive black hole eating the gas. So I'm going to play this. So those different tones that you hear are the different colors of X-ray light coming from different supermassive black holes eating a whole bunch of gas and shining really brightly. I love that. I think it's so cool. Another way that we have to see black holes, especially supermassive black holes, is to look at the effects they have on nearby orbiting stars. So this is a picture that's taken of the center of our Milky Way galaxy. And each of these individual rainbow dots is an individual star, like a star. And the white star at the center, this is where there's something very special. And what I want you to watch, if you are in the Zoom room as opposed to watching on Facebook, you can move your window so you can see this top corner here with the year. And as I play this is almost going to be like a flip book where we took pictures of the center of our galaxy every year to see how the stars were moving. And now if there were no supermassive black hole there, the stars would move in straight lines because there'd be nothing to change their path. But if we have a supermassive black hole that's very, very massive at the center of our galaxy, its strong gravity can actually bend the path of the stars as they're moving. So let's watch this. It starts in 1995 and it's going to come all the way up till 2020. Here's 2000, 2005. And you can see they've traced out the path of the stars with the dotted lines. And some of them are very clearly being slingshotted around. 2015 and 2020. So we see this one star in particular has been able to make almost 2 full orbits around this point at the center. And there's nothing coming from this point in the center. The white star is just for our eye, but there's no light or signal of any kind coming from right there in this image. But we see the effect that its gravity is having on the path of all the stars nearby. And this is how we figured out that there is a supermassive black hole at the center of our galaxy. And it was this discovery that won the Nobel Prize in Physics just the other year, which is very exciting. So this black hole at the center of our galaxy is called Sagittarius A star. And it is 4.3 million times the mass of the sun. And the million with the small m, not a b, but still very, very big. 4.3 million, again, this is 11 days compared to 16 minutes, still very big. Another way that we have to see black holes is of them smashing together. But when we're looking at black holes this way, we're not seeing any light coming from them. We are instead seeing something entirely different called gravitational waves. And we have to use special detectors to see these because telescopes don't pick them up. But gravitational waves happen when we have 2 black holes that are spiraling around each other, they're orbiting around each other, and they're getting closer and closer because their gravity is slowly pulling each other in. They're falling in together. And as they get closer and closer, they make more gravitational waves until they smash together and you get this ripple like in a pond. So there's no light at all coming from any of this. But instead, we can just see this yellow and blue. This is showing what the gravitational waves would kind of look like to help us imagine it. And as they spin closer and closer, they make more gravitational waves. They have this burst at the end as they smash together, and then it's just quiet. And so these 2 black holes merge together to become one bigger black hole. So the way that we detect these, as I said, we can't use telescopes because there's no light coming from any of this. So we use lasers. We built really cool detectors that use lasers. And we split our laser beam so that we have identical laser beams, but go down 2 different parts of an L. They reflect off of a mirror at the end and they come back together. And if the paths of those 2 distances are exactly the same, then the lasers will come back and they will add together in a certain way. So they'll be bright or dim depending on how their path changes. So if the distance between these mirrors changes a little bit, we'll see a flicker in the laser beam. We'll see it get brighter or darker depending on how the laser light is adding up together. So we have to have very specific lasers and very careful detectors in order to be able to measure this super well. And we have to use not only just the one detector, but we have 2 detectors with LIGO. There's another one in Europe, and they're building more in India and I believe Japan as well, so that we can look for more gravitational waves, because the more detectors we have, the better we're able to pinpoint the location in the sky. So the first gravitational wave was detected in, I believe, 2015. And this was incredibly exciting. We've long suspected that gravitational waves were happening, they existed, but we didn't have true evidence of them until the 2010s. And Einstein predicted these back almost 100 years ago. So here we have the signal of the gravitational wave. You see that wave pattern there and how it gets bigger and bigger. And then there's kind of a big bit at the end, and then it kind of ripples out at the end. This part right here is when they smash together. And so we see this from the 2 different detectors in orange and in blue. And when we line them up together here at the bottom, we see they match super, super well because they're coming from the same black holes mashing together. They're not completely the same because they're different detectors. One is in Washington State up by Vancouver, and the other one's all the way down in Louisiana, down by Texas and Mexico. So they're very far away. They have different noise patterns, but the signals line up super nicely. So we have another sonification that I'm going to play for you. Hopefully you will hear it. And this is what's called the chirp. So this is taking these gravitational waves and actually turning them into sounds that we can hear them. Again, I've got the link here. So when you look at a PDF of this shared later, you'll be able to go back and listen to it. So here we're going to show, it goes pretty fast, but it'll go a couple times. We've got LIGO Hanford up top and LIGO Livingston at the bottom, and they're lined up so they chirp at the same time. It's first going to play at a lower tone, and this is the actual frequency of the gravitational waves. And then they put it up into a higher pitch band that's easier for us to hear. So cool, hey? So those are gravitational waves. But the signals look a little bit different depending on which black holes you're looking at. So even though the only thing we see are these waves coming to us, we are able to tell a whole bunch about the black holes that made them. So when I play this next video, what I want you to pay attention to is how the different sizes of so those blue dots are the black holes, and then you're going to see the gravitational wave pattern beneath them of the black holes spiraling into each other. I want you to pay attention to how the sizes of the black holes affects the shape of the waves, how tall it is and how fast it is. Okay? We'll play it a couple times. There's no sound associated with this. So we see with this one, it's got small black holes, and so it's wiggling very small amplitude. And this one over here had quite big black holes. And so it had much taller amplitude and kind of slower waves as well. These ones were closer together, so they're spinning faster and faster. So we see that when they all chirp together, they all have this kind of getting faster and louder and faster and louder and chirp, and then kind of ripples in a pond to quiet. And all of these black holes are two smaller black holes that add up together to make a bigger black hole when they smash together. And so even though the only thing that we see is these gravitational waves, this wiggle, that's the only thing we see with our detectors. But since we know about the shapes and sizes of black holes that would make these waves, we can figure out how massive those black holes were beforehand and how massive the black hole is at the end, the merged one is. We'll watch it one more time. So you can see how the sizes and distances of the black holes affects the gravitational wave signal. The final way that we have to see black holes is when they get in the way of stuff and they bend light from behind them. So here we have an image of a galaxy, and superimposed in top with a computer is what it would look like if a black hole were in the way. And black holes, since they have such strong gravity, they bend light in a really funny way. And so it's not just like there's a hole in the way, but it magnifies and distorts and kind of bends the light all around it. So if we're taking a picture of a galaxy, we know what galaxies generally tend to look like, but we instead see, for example, a picture like that with a spot in the middle and a ring around the edge, and we say, what is that? This gives us an idea that there might be a black hole in the way, in between us and the galaxy in the back. So here on Earth, this is us over here on the right. As we're looking at distant galaxies far off in the universe, there can be sometimes a black hole, often a supermassive black hole with a whole galaxy along with it. There are many of these throughout space, outside of our galaxy, in between other galaxies. And if we're looking at a distant galaxy, sometimes a black hole that's in the way can end up bending the light, and not only bends the path of stars, but it can also bend the actual path of light itself. And it bends this light such that we can actually get multiple images of this distant galaxy. So even though the distant galaxy is behind it and there's only one of it, because of the way that the light travels, it appears as though there's like, for example, a bigger one down here and a smaller one up here. And we know from how gravity bends light, we can reconstruct this with computers to figure out what the galaxy behind it must look like. And this can even almost act like a magnifying glass because it can help us to see fainter signals from further away. It kind of boosts them a little bit as the black hole acts like a magnifying lens, so we can see more distant galaxies, which is very exciting. And this process is called gravitational lensing, because the gravity acts like a lens for the light, the gravity of the black hole. So this can end up with really cool images where this dot here, it looks like it might just be a star or something, but actually we know that this has to be a supermassive black hole and its whole galaxy along with it because of the way that it is bending and distorting this image around it. So this is a normal type galaxy that is back behind it, but since there's a black hole in the way, it bends the path of the light and we get this cool ring shape. It's almost a complete ring. And so the strong gravity of the supermassive black hole, it acts like a lens bending and distorting the image. And this also gives us perhaps one of the creepiest, one more image. We can also sometimes get what's called an Einstein Cross, where instead of having a ring all the way around it, you could have 4 images, one on each kind of side. And this also, there is a black hole in the center, and it's imaging and it's lensing light from a more distant galaxy behind it. So the black hole in the way, in the middle of us, we can use the construction of what the galaxy looks like and what we expect it to look like to figure out how massive the black hole is and where it is in between us and that thing. And gravitational lensing has given us perhaps the creepiest ever image that I have seen from space. Looks like a smiley face, where we have 2 galaxies that are lensing these images of further distant galaxies, and you get this creepy little clown smiley face. And one thing I want to point out that's really cool is that each of these individual dots, these are all galaxies. This dot here is a star. We can tell because it's so bright, it has this kind of cross pattern, but all the rest of these are their own individual galaxies off in the distance. This one we can see really nicely. So this is super cool. So in conclusion, for how do we see black holes? We can take a picture of them directly using radial light. This was only possible in the last couple of years. We can see them eating their star friend or eating other gas. We can see the effects they have on nearby orbiting stars. We can see them smashing together. We don't see them with light, but we see them with gravitational waves. And we can also see them bending light from behind them. So with that, it's Q&A time. So please put your questions in the Q&A feature. Again, the chat is for technical stuff. And I want to leave you with this cool movie poster. NASA commissioned some movie posters of different extreme cosmic phenomena, and black holes were one of them. So it says Cygnus X1 presents Devoured by Gravity. And if you'll remember, Cygnus X1 is the first black hole we ever saw. It's dinner time and you're the meal. Pretty exciting.
Thank you so much for that amazing presentation. I'm really excited about that. That is awesome. And
thank you so much.
As Dr. Abbie mentioned, if you have any questions, please put them into the Q&A function, and we will answer them during our Q&A session, which starts right now. So let's start rocking these questions.
Yeah.
First question, has anyone calculated the escape velocity of a black hole, or is it infinite?
Yes, so we can calculate the escape velocity of a black hole given the mass, but the escape velocity is faster than the speed of light. And this escape velocity is just a number. But if that number is bigger than the speed of light, it means nothing can actually go that fast, so can't get away.
That's awesome. Is there a dark area in between the photon sphere and the accretion disk?
There can be, yeah, there can be this like black hole shadow a little bit. One of the cool things, I don't know if anybody here saw the movie Interstellar, but there was a real astrophysicist who was involved in consulting on Interstellar. And since Hollywood has access to such cool computers, we were able to do actual science as they were making some of the images for gargantuan, I think was the name of the black hole there, that they get really close to. And we were able to actually get a scientific paper or two out of making this background image to CGI into the movie, which is so, so cool. And one of the things that they found with that kind of detailed computer simulation is that you can get this black hole shadow that is a little bit different from where we have this little photon sphere, this like final little kind of last hurrah, and the accretion disk, which is like stuff and it's light hanging out. And the accretion disk lasts for a very long time. So when we're looking at these things, like in space, like when I'm looking at these things, the black holes that I'm looking at, the black hole and its star and the accretion disk and everything is just a single pixel. It's 1 point. So the only way that I can see what's happening is by looking at the brightness and the color of the X-rays. One of the only black hole that we've ever been able to take like a detailed picture of is this M87 star of a nearby galaxy. All of the other black holes that we see are single individual pixels. We have no image resolution on them. So we've not been able to take a direct picture of all of this additional kind of photon sphere separate from the shadow, separate from the accretion disk, but you can see a little bit of the shadow in with the accretion disk in the M87 star picture from the Event Horizon Telescope.
Wow, that's awesome. We have a question. Are the relativistic jets created because of all the matter trying to go into the black hole and the matter is instead being squeezed out?
Somewhat, yes. So black holes are very messy eaters. If you remember Cookie Monster is trying to eat all of the cookies, but he makes a giant mess and cookies kind of fly everywhere. Black holes are the same way with stars. They're collecting all of this gas like a dinner plate around them. They're sitting in the middle of their dinner plate, but they're such messy eaters. And there's so much kind of energy being released as the stuff gets closer and closer to the black hole. All of this stuff also has magnetic fields. So the same kind of magnets that stick to your fridge, or like the Earth has a north and south magnetic pole because the Earth itself has a magnetic field. Well, all of this gas from the star also has magnetic fields to it. And a lot of times when astronomers are trying to figure something out, just at the first time we figure it out, we kind of pretend that magnetic fields don't really exist, but this isn't real. So we have to actually think about magnetic fields afterwards. And the magnetic fields almost act kind of like Spanx in that they hold the stuff in together and it can support a lot more matter than what would otherwise maybe blow away. So as this matter is coming together in the accretion disk and it's swirling around, it also has all these magnetic fields that are helping to support it. And as it gets closer and closer to the black hole, these magnetic fields can end up spiraling around a little bit and supporting these kind of collimated outflows, we call them. So it's like a fire hose, like a pointed fire hose of material that is shining really, really bright light in all the different bands. It can shine X-ray light, infrared light, visible light, radio light, all the way up and down. And we have this really energetic particles that are moving super fast and they're shining a lot of light as well.
Well, that's
black
really
holes
cool.
are messy eaters.
Yeah, I really like the Cookie Monster analogy. It's making me hungry. Do black holes have to be rotating to support having polar emission jets?
Well, they do need to be rotating a little. Well, okay. I'm not sure if the black hole itself needs to be rotating. All of the accretion disk matter needs to be rotating. Black holes, though, generally do have some spin to them. So black holes have only two properties. They have a mass and they have a spin. So they're like spinning, just like a top. And they don't have anything else. They don't have an electric charge. They don't have their own magnetic fields, all the stuff around them that has a magnetic field. And this is called the no-hair theorem. So there's not any additional fluff on the black hole. It's just the mass and the spin. And it's very, very unlikely to have a black hole with the spin of 0, to have absolutely no spin, since it was formed from a collapsing star, or it was formed very early in the universe, and it's adding all this stuff. And as it is slowly eating the matter from the star, it's also getting a little bit of what scientists call angular momentum. It's getting a little bit of the spin kick from all the stuff it's eating, and this tends to cause them to spin quite rapidly, we think. So the black hole is spinning and all this stuff around them is swirling together. And this is part of what helps to, we think, have the magnetic fields in a way that can support these big jets.
That's really interesting. Somebody asks about primordial black holes. Can you have black holes the size of an atom?
So primordial black holes are a really cool idea, but they're not something that we've been able to see. So the idea of primordial black holes being something that could have started primordial being very like as the universe was formed, you could have these super tiny black holes. So like less than the size of an atom, even smaller than a proton. But the thing is, if a black hole were that small, then it can't, that not even like a subatomic particle can actually go inside of it. Like it can't accrete anything. Nothing can fall into its event horizon because the event horizon is too small. So nothing can fit inside of it. And so eventually it'll kind of evaporate and go away. So if they exist, they probably evaporated pretty quickly, in my opinion.
Okay. Yeah, I've always been curious about that.
Yeah.
Given the two revolutions around Sagittarius A, has the orbit size been calculated?
Yes, it has been calculated. I don't know it off the top of my head, but we do know the size of the orbit of that star.
Neat.
Yeah. I bet the Wikipedia page has something. If you look at the Sagittarius A star, that star in particular that we saw the two orbits of, I think it's called S02. It's a very exciting name. I'm sorry, I know. But I bet there are some scientific papers that have that up there.
Perfect. Yeah, I think sulfur dioxide there for a second.
Yeah.
Why aren't there any ripples detected after two black holes smash? Why does the line go straight all of a sudden? I think this is in reference to the gravitational waves.
To the gravitational waves. That's because there's no more gravitational waves being emitted. So the gravitational waves are only happening when we have two different sources of gravity that are moving around each other. And so once the two different sources of gravity, the two black holes, have merged together to create one stable black hole, then the gravity isn't moving or changing. And so it's not producing gravitational waves. So again, think of it like a ripple in a pond, where when you throw in the rock, as it first is hitting the pond, you have this big wave. But once the rock is in, there is no more rock hitting the pond. And so it's not creating additional waves. The wave that exists just kind of goes out.
Awesome.
And one cool thing to keep in mind is that these gravitational waves have always been happening and they've always been existing. We've only just recently been able to detect them. But there's gravitational waves that are like probably going through your body right now, which is really cool to think about.
That is very cool. A little bit
frightening. But we don't know. We would never have guessed until we built LIGO and Virgo.
Exactly. I'm excited if they're going to ever build LISA. I think that will be.
LISA would be awesome. For those who haven't heard, LISA would be the laser interferometer in space. So you would have some different satellites that would be flying in formation, in like a specific formation, and they would bounce the laser beam between them. And you could get to be quite big distances there, since you don't have to like build tunnels underground like we did with LIGO and Virgo, Virgo being the European one. And so when you don't have to like make ground perfectly flat and build these giant tunnels with these lasers through them, that took quite a bit. Building spacecraft and launching them on rockets is also a big deal, but you can have them at much farther distances. So when you have these bigger distances, you can detect different weights of black holes merging together, which is very exciting.
That's super awesome. Do you know if NICER will be saved before the International Space Station is decommissioned? If not, do you think the loss of this telescope will impact X-ray astronomy?
That's a great question. I don't know about that. I'm not on the like commissioning and technology team for NICER. So NICER is like fixed to the space station. So there's no way to have it be up there without having a space station up there. But we have a bunch of other X-ray telescopes that are in space right now. The thing is, though, even though we have all these different X-ray telescopes, they're all looking at different types of X-rays or in different ways. So like Chandra, for example, the Chandra X-ray Observatory that we did that beautiful astrosonification with, that's really good at looking at faint things that are far away. But if you were to use Chandra to try to look at a bright black hole in our galaxy, it would blind it. And NICER is great for looking at bright black holes in our galaxy. So if NICER goes away, we would definitely lose out on cool black holes and even these neutron stars and pulsars and all kinds of stuff in our galaxy. We'd really lose out on a bunch of that cool science if it goes away. Yeah.
Interesting.
Yeah.
Somebody asks, I've heard that even though radio telescopes are observing very energetic objects, the amount of energy they actually collect is a small fraction of a watt. Gravitational waves are caused by even more energetic events, but it sounds like the amount of energy detected is even smaller.
Yes, that's correct. The amount of energy detected is very, very small. This is because the thing that's producing the energy, it's sending out this energy kind of all the way around for the most part, like all the way around as a sphere, and it expands out through the universe. So as we are some tiny, tiny fraction of all that energy that's come out overall, we end up detecting a very small part of it. So even though it's an energetic process that produces it, it's not like we're getting totally blasted with gamma rays, for example.
Awesome. Will the James Webb Space Telescope help in viewing black holes?
It will, and you're going to hear a lot more about this from Dr. Greg Sivikoff next month, so I don't want to spoil the surprise, but it will in very cool ways, and you'll have to tune in next month.
Awesome. That's perfect. How do you translate the radio signals from the Event Horizon Telescope to make a color photo of M87 Star?
Oh, so this was over a year's worth of work from hundreds of scientists all working together. They're using computers, in short. They have ways that they can correlate the radio signals that they get. And these radio signals, it's not like they're listening to the radio, right? It's not the sound waves, but it is the actual information that travels to, like, your car radio, for example. There's the information traveling through the air on radio waves, and then your car radio turns that information and makes sound come out of it. Because when the radio waves coming through the air, like, you can't hear the sound in the air, right? So the same thing is happening with the radio telescopes detecting the radio waves from space. And we have ways of correlating. It's called the radio waves from all the different detectors, because again, we have them across the whole Earth. We have ways of correlating all of that together. We're using big fancy computers and a lot of computer software that we write ourselves. And they have a bunch of special software that they developed in order to correlate those radio waves and make a really cool picture.
That's really exciting.
Yeah, if you go to the Event Horizon Telescope website, they have a lot more specific information about how they do that there.
Awesome. I think I might check that out. That's really awesome. Since black holes are actual holes in space-time, what is happening when two collide? What about the energy release? Is it all gravitational energy?
When it's just two black holes, it is all gravitational energy, because we've looked at it very carefully with like light telescopes and not seen it. On the flip side, when there's been two neutron stars smashed together, those also emit gravitational waves. But neutron stars have a surface and they've got like stuff that we can see. Their escape velocity is less than the speed of light, so light can get away from it, so we can see them. And when two neutron stars smash together, we get what's called a kilonova. And this we can see very well with a bunch of telescopes across the electromagnetic spectrum. And this was super exciting because it also confirmed that we can see these gravitational wave signals when they're supposed to produce light. And we don't see them when they're not supposed to produce light. So everything is working as expected. What was the rest of the question?
I clicked answer on it, so it's.
Sorry about that. Type in the rest of it if you had more to it. I got excited about the neutron stars and forgot the rest of the question.
Oh, no worries. That's great. Yeah, it was just about what is happening when they collide. Is it all gravitational energy? So.
Yes, it's all gravitational energy. So most of the energy is kind of kept within the black holes and it makes the bigger black hole, but some of that energy gets radiated out in the gravitational waves. And the one way to think of black holes, we call it a hole because we're thinking about like the night sky as like a flat plane and it's like a hole in there. But a better way to think about them is like a sphere. So they don't actually have like a top and a bottom. They have an outside and an inside. So when they're smashing, it's like if two stars were to smash together in some sense, except that we can't see, like there's no light coming from this. And it's their event horizons merging instead of their surfaces. But you can kind of think of it like two balls of stuff smashing together, I think, roughly.
That's exciting.
Yeah.
how many stellar black holes are there in the Milky Way, and how would you estimate that number?
Great question.
Do we have a count?
I'm trying to think. So of black holes that we have seen, I would say there's on the order of like 50 to 100 that we've seen. We expect there to be thousands, if not millions. And the way that, but like, again, we can only see the black holes when they're doing something with something else to shine light in our direction. So they have to be eating another star or affecting the path of a different star, or getting in the way of us looking at something else. Like, it has to be doing something with its environment for us to see it. So a bunch of them are just hanging out by themselves and we can't see them, and we're never going to see them unless they do something with something we can see. The way that we estimate the number of black holes is by looking at what's called stellar populations. Since these are stellar black holes that are formed from dead stars, we look at how many stars we expect to be formed and what the star formation rate is. So how many baby stars are being born in a given year throughout the galaxy. And then we look at how massive those stars are. We tend to produce a lot more small stars like our sun, and only a couple really big stars that can eventually form black holes. But these big stars die much sooner than small stars. So our sun is going to live for like 13 billion years or so. It's going to live for about 9 billion years or so. 13 billion is the life of the universe. 9 billion years or so, and we're about halfway through that right now. So our sun has been around for about 4.5 billion years, and it's got another 4.5 billion to go. So we're doing great. But massive stars that turn into black holes, these only live for hundreds of millions of years. So this is hundreds of times shorter than the low mass stars. So these are kind of like burning up hot and bright, like live fast, die young type thing is their kind of motto as they go through life. And when they form these black holes, we can kind of try to look at computer populations of how many stars are being formed, whether or not they're big, how fast they're living, that kind of stuff. So we have to take a lot of information into account to figure out how many black holes we think are in the Milky Way.
That's really neat.
Yeah.
Yeah, we have a lot of questions, so we'll try to get to as most of them as possible.
Sure thing.
Here's a great question. Do black holes relate in any way to dark matter and dark energy?
In short, not really. Dark matter and dark energy are things that we think about on entire cosmological scales. Cosmology meaning the entire whole universe altogether. And black holes are a very, very small part of that. These are physical objects that are within a galaxy or at the center of galaxies. There's many galaxies, but these are physical objects within there. And we've done some calculations, not me, other people have done some calculations to figure out that black holes cannot account for the kind of missing matter, this dark matter that we can't see, but that we know is there. Because there's dark matter in galaxies, but the mass of the black hole at the center does not account for all of the matter that we can't see. And it's not distorting the path of the gas, and it's not eating other stuff. So it's very likely not black holes. There's some really cool ideas of what it could be. There's these particles called axions that might be involved in dark matter and dark energy. I will leave you to do some internet sleuthing on those. There's a bunch of other candidate particles for dark matter. Dark energy is something we understand even less, but it's an even bigger part of the universe. And I think I'm going to not really get into it because it's very confusing and we don't have a good idea at all. But it's not just me not having done my research, it's scientists in general have a very poor understanding of what dark energy actually is. We just know that there's a lot of it.
Yeah, for sure. And to all of our audience today, we will be having a dark matter specialist, Sophia Nasser, coming to Calgary in June.
Oh, fantastic. She's wonderful.
She is. She's great. So stay tuned for that.
Perfect.
It's an exciting presentation. Let's move on to another question. This one's another fun one with relativity. Does time stop near black holes? And if yes, how do black holes eat?
So black holes do weird stuff with time. So you're right on that for sure. Not only are they bending space and they can bend the path of light, but time behaves really weirdly around them too. And our understanding of how this works all comes from math. So again, we haven't ever sent a probe to a black hole. They're really far away. The furthest thing we've ever sent out from Earth are the Voyager probes, and those have kind of only recently reached the edge of the solar system. And we have quite a ways to go till we get to just the nearest star, and the nearest black hole is well beyond our stellar neighborhood. So all of this that we understand is from stepping back and looking and then doing a whole lot of math. And so time slows down around black holes, but not for the person who's there. So the way that we imagine this in like university physics, when you start to learn about relativity and how time gets affected, is we call what's called the twin paradox. So you come up with this idea of if you have two identical twins, you have one that stays here on the Earth and one that gets in a magical spaceship, flies around near a black hole, and then comes back. The twin that comes back after it's been flying around near the black hole, it will be younger than the twin that stayed on Earth. However, the twin, its own experience of time hasn't changed at all. So it's only that it's relative to the person who stayed on Earth that they have aged less. Actually, I have to say the movie Interstellar handled this quite nicely when they go down to the tidal planet to try to rescue their colleague, and then they come back. I haven't given anything away with that, but the way they handle how time changes is handled very nicely, in my opinion. It's very cool. So as the stuff gets closer to the black hole, it's still hanging out, and in its own relative frame, just compared to itself, time is happening normally. Its clock is ticking along. If you had somebody who's super far away, it would look like their clock of this little particle going close to the black hole, their clock would look like it's slowing down. But to the particle itself, hanging out and looking at its own clock, it's like ticking along normally, just like no problem. So as something gets closer and closer to a black hole, it gets into stronger and stronger gravity. And it's this stronger gravity that causes time to slow down more and more and more. So as the particle falls into the black hole, it falls into the black hole. It's ticking along with its little clock, and it's ticking along, and then it reaches the event horizon, and it falls in. However, since time is slowing down for somebody who's like really far away, as time is slowing down, it looks like time is slowing down more and more and more. And it has this final image of the particle as it's falling in. And it's like this ghost image that appears, and it's going to stay there kind of forever, basically. And so, but that only exists for the person or the particle that's looking really far away, because it's only relative to the one really far away. The particle that falls in, it like falls in and it goes on, because we know that black holes get bigger. We see them, like we can measure them, and they get bigger when they eat more stuff. So that's happening. But it's all, the idea of relativity is that it depends who's measuring it. So it's not just it's not just the person on Earth who kind of their measurements matter. The person who is, or person or particle that's going into the black hole, their measurement frame is also important to take into account.
Oh, that's really cool. That would have helped my
it really messes with time. Yep.
That would have helped in my grad level gravitation class for sure. I appreciate that. No, that's awesome. So what are some of the next steps that will occur soon to get even better radio imaging of black holes? Is there any plans?
So I think I'm pretty sure there are plans. I'm not involved with them, but I'm pretty sure there are plans, because astronomers love making plans for what we could do next even better. There are some things we could do with like what's called the next generation very large array, which is a big array of radio telescopes, all these different radio dishes, and they want to improve it and do an even better, bigger job with that. And also this involves updating the computing backend, as we call it. So all of the supercomputers that they use to run their stuff and to correlate their data, we have to have the top-notch stuff for that so that we can process all the data. Because radio telescopes collect a ton of data and they throw away most of it, which is surprising. Because in X-ray astronomy, we get so little data that the thought of throwing away a photon kind of makes my heart twinge just a little bit. So they are working on ways to take more and more data to get clearer and clearer images, but we can only really do it for this black hole that's very close to us. Because again, this imaging power is absolutely ridiculous in order to be able to see that. And so we can try to look at the supermassive black hole at the center of our own galaxy. It is closer to us, but there's more like gas and stars and stuff in the way, so it's harder to get a clear picture. Otherwise, one of the things that would help us best be able to take clearer images of black holes is to put a radio antenna dish on the moon, which is not ridiculous. We have put a mirror on the moon so you can bounce a laser off of it. And this is like a thing scientists do sometimes to calibrate things and to check things. I don't do it, so I don't know the details. But if we were to put a radio antenna dish on the moon, then we could have an even bigger, what's called a baseline. So the distance between the things, the bigger your baseline, the distance between your antennas, the smaller resolution you can get. So if you want to campaign for a radio antenna dish on the moon, I'm all for it. But there are no plans for that right now.
Totally. I'd be in for that too.
Or like put one on Mars. That'd be amazing.
Oh yeah. God. Yeah. Have it stretch across the whole solar system. That would be amazing.
That'd be awesome.
Here's a great question. It comes from a grade 6 student, and it's actually a question that I've always wondered about as well. So I'm excited for you to speak about it. If you were to grab a black hole and put it on a table and shine a light on it, would there be no light?
There would be some light, but like you would have the light coming from the light bulb because the light bulb is still up there. Like it's not, the light bulb's not in the black hole. So the light bulb's still shining. So you'd see your table, but there would be this like funny lump, but it wouldn't be a perfect circle, but it'd be a kind of a ball, but it'd be so black that you couldn't see like the height or the shape of it. There's this paint called Vantablack, which some artists have used to paint things, the blackest, darkest thing with no reflection at all. And it looks wild, the things that are painted with this, because even things that are black, we're used to still seeing like the shadow of the light here versus there. And with the black hole, we wouldn't see any of that. So you would have this like funny, lumpy, almost bean shape because of how it's bending the light as it's going around it. It wouldn't be a perfect sphere, which is weird to think about. But there you'd have what looks like a hole in your table, and that part would be black.
Sounds like an IKEA table I've purchased recently.
Exactly.
Here's a great question. If black holes continue to accrue mass, do they expel it at some point? And basically, what does the end of life of a black hole look like?
So there is this theoretical idea called Hawking radiation, where black holes can lose mass, but this is a tiny, tiny amount of mass. And it doesn't nearly compare to the amount of mass that we see black holes eat from eating a star or eating a bunch of gas clouds that are nearby them. That's like significant mass that they're eating over time. And this Hawking radiation is just tiny, tiny amounts of matter that they're able to able to get lighter with. And they're not actually expelling anything from inside because nothing can escape from inside a black hole. But Hawking radiation is where you have a particle and what's called an antiparticle, which has like negative mass in some sense, created just outside the event horizon of the black hole. And the particle shoots off and it escapes, but the antiparticle goes inside. This kind of like subtracts a little bit of mass from the black hole. But again, that's like at a particle by particle level. And these black holes are eating stars. Like that's a lot of particles, and you don't get Hawking radiation to get rid of that. So black holes can effectively never die. They're like vampires. They're never, ever going to die. And eventually the universe is going to get taken over by black holes, which if you like black holes is a super cool idea. They just kind of keep eating stuff. If it comes close to them, they're going to eat it. And one other thing to keep in mind is that black holes aren't like vacuums, like suctioning stuff up and like sucking things in. It's just like a hole in space that things fall into if they get too close. So it's like if you have a giant, like a giant soccer field, which is like space, and you have a big gopher hole somewhere, you don't necessarily know that the gopher hole is there if you're just standing on the edge of the soccer field. It's only by running around. If you happen to get really close to the gopher hole, then your foot might fall in and you might hurt your ankle. But it's only when you get super close to it that you would even know that the gopher hole is there. So it's only by getting really close to the black hole that anything would fall in. So that's why this danger zone is like incredibly small. For example, if you were to somehow magically wave your magic wand and replace our sun with a black hole of the exact same mass, the Earth would keep orbiting totally normally, like nothing had changed. Even Mercury would be completely fine. We wouldn't have any more sunlight, so that would not be fun. But the gravity would be the same because the mass is the same at this distance. The danger zone for that black hole would be well within the current size limit of the sun. So it's super tiny. So we have nothing to really worry about. We can just sit back and enjoy.
Thank you so much for answering that. That's a question that I get a lot from the kids on Saturday mornings when they ask about that. And I just remember my relativity professor just screaming, "Black holes are not cosmic vacuum cleaners. Just chill out."
Black holes don't suck.
Exactly. What has been the most exciting telescope you have ever used, and what would be your white whale telescope to use?
I have to say, I think Nustar is one of the most exciting telescopes I've ever used because its like superpower is that it can stare at really bright things without kind of blinking in some sense. So oftentimes telescopes have these sensitive detectors on the back, and the telescope is to collect light to put it on the detector. And then the computer reads that out, and that's how we get our data. And so oftentimes the detectors are very sensitive because we're looking at faint stuff that's really far away, right? But if something super bright and energetic and exciting happens, you can't look at it with your detector because you'll like overwhelm the detector and you might break it. And that would be super bad. So you have to sometimes use these like limited modes to like kind of look at it almost like it's through like crossed fingers. The detector's looking at the thing, which isn't very exciting. Or like you can collect all this light, you can count all these photons, but you can't actually get your data down fast enough because your data has to be sent down via what's called telemetry. And so the information has to go from the satellite to the ground stations. And if you don't have enough bandwidth to get the data down, then you have to dump it. You can't use it. And that's super sad when that happens because you've counted the photons, but you can't have them. So Nustar has been really fun to use. And I actually, my favorite data so far has been using Nustar and Nustar together pointed at the same thing at the same time. Because Nustar looks at these low energy X-rays and Nustar looks at the high energy X-rays. And so you get this huge, beautiful color spectrum of your source, and you can look at them changing really quickly. So I love the combination of the two. But my white whale telescope would be this thing called Strobex that I'm on the steering committee for. We're always planning for the next telescope because it takes about 15 to 20 years from being proposed to being launched. This is a very long time, right? So Chandra, which is currently still being used, it was launched in 1999, which is before like some of our graduate students were born even. So they're around for a long time, but you have to propose them super early. The Hubble Space Telescope that we're still using was proposed back in the 1970s for launch in around 1990. So it takes us such a long time to get the money for these telescopes because you have to get multiple nations to agree on something, build a telescope, put it in a rocket and launch it. Like that's a lot. So Strobex is something that we've put together in the last couple of years that we are proposing as a medium type mission to NASA right now. And it would basically have a super Nustar component, and it would have not quite Nustar, but similar high energy coverage, and to be able to stare at the brightest, coolest stuff in the sky without blinking. And I think it would be just the most incredible thing if it got built and funded. I think that'd be awesome.
That does sound very awesome.
It would be launched in the mid 2030s, I believe.
Wow.
Which is a long ways to think about.
Yes, that does sound
we plan
scary.
Very far ahead. Yeah.
And graduate students from 1999. That makes me feel old.
Yeah.
Do you know the current status of the Event Horizon Telescope work that provided some of the first radio views?
So the Event Horizon Telescope is actually a consortium or collaboration that uses a ton of individual small telescopes. And when they combine them all together, they call it the Event Horizon Telescope. I believe they're still working and looking at stuff. I'm not part of that collaboration, so I'm not privy to all of their emails. But I believe they're still working on some of the Sagittarius A star stuff. And it was only in the last, maybe it was 2020 or so, that they announced the polarization results where they could show us the magnetic field around the black hole. So they are still looking at their data. Yep.
That's cool. I've got a fun question here. And I seem to remember that gravitational waves, we actually pinpointed the location of a potential merger. And this question kind of goes along with that. Is LIGO able to determine where or how far away the merging black holes are?
Yeah, so they are somewhat able to. The more detectors you have spread out, the better you're able to pinpoint the location. So for example, to be able to triangulate a signal, you need 3 detectors to make a triangle to triangulate. And LIGO is only 2 detectors. So they can't pinpoint a part of the sky, they pinpoint like a swath of the sky. And it's kind of a big part because it's only 2 detectors. So since Virgo was also online, by knowing that Virgo couldn't see it, like these detectors do have some blind spots. So if we say it's within this area and overlap that with Virgo's blind spot, and it has to be within this smaller area. And that is how we're able to do that. So by having the LIGO, 2 detectors, and Virgo, we're able to triangulate the sources in the sky. By adding one in India and by adding one in East Asia, we are also going to be able to further figure out where these are. And that way, when one detector goes offline for maintenance upgrades, which have to happen, of course, then you're not going to lose out on pinpointing signals.
Interesting.
And also, if we want to do follow-up to look for light coming from there, we call this electromagnetic follow-up. When you want to look at it with a telescope like Hubble or with Chandra or with JWST, you have to have a super, super small area to look. Otherwise, you're just like scanning across the area. And this takes a lot of time. So if you have a quick signal, you don't want to waste your time on that. So the more detectors we have for gravitational waves to better pinpoint a smaller area, the much better we'll be able to do with follow-up of the light studies.
Awesome. Yeah. It sounds like me trying to find some dim Messier objects with my telescope, just scanning and finding nothing.
Exactly. You're just slowly scanning. You're like, it's somewhere in this range, and but you only have this little view. So you just scan across, scan across. Yeah, that's what we do with just bigger, fancier telescopes. That's it.
Awesome. Here's an interesting one. Are black holes found near the edge of the galaxy, or mostly in established or older parts where stars are formed?
So the supermassive black hole is at the center of the galaxy, but it's not just the supermassive black hole's gravity that holds the galaxy together. It's also all the dark matter that's around it that's holding the gravity of all that's holding it together. So the supermassive black hole is at the center of the galaxy. And this is true for all the ones that we've seen. So we assume it's true probably for all of them. That's how the math would work out. For the stellar black holes within the galaxy, these tend to be within populations of older stars. So this is where you've had star formation of massive stars, but they've aged. So we have these pockets of star formation throughout the galaxy. It doesn't have to be only at the center or only at the edge, but you tend to find them in pockets of where you've had older stars happening, where you've had these young stars age and then die, of course. For us, since we are a bit further out in the galaxy, if we look towards the galactic center, there's a lot more stuff over there, because that's where like the rest of the galaxy to the center and the whole other half of the galaxy is all over that way. So most of the sources that I look at are towards the galactic center, meaning that you would look at them in the southern hemisphere, because that's where you can see the galactic center. There are, of course, some sources in the other parts of the sky. There's just fewer stars over there, so you have less chance that you're going to have a black hole over there.
Cool. That's great. I do see that we're approaching 9 o'clock, but we do have some questions still open. So okay. We'll continue until probably just after 9:10, and then we'll close the meeting. So
sounds good.
Here's a question I find interesting. This person asks, I've heard something about charged objects being accelerated by the gravitational pull of a black hole, and this accelerating charged object emitting X-rays. Is that right? And can you explain that phenomenon?
So this sounds like the particles that are in the accretion disk, these kind of little particles of star stuff that the black hole's eating. They get swirled around in the accretion disk, and they have their magnetic fields that are lining up or anti-lining up together and locking in. And then some of them get accelerated along the magnetic field lines in these big jets. and they get launched off and they shine really brightly. So if they're launched from close to the black hole, they shine X-ray light. If they're launched from really far out, they shine radio light. And then we have kind of a spectrum in between. So you have infrared is like a little bit further out. Visible is a little closer from that. So yeah, when you have these charged particles that are accelerating around, these are tiny little particles, like subatomic particles. As you have these accelerated by the magnetic fields and shooting out, this is how you can get your jet light.
That's really
yeah.
Cool. Somebody asks, do you know how far the nearest black hole is, and any theories as to the total number of black holes in the visible universe? Is it, do you think it's about equal to the number of galaxies, or we're not really sure?
So there's a couple parts to this. So for the nearest black hole is probably one that we can't see, like, right? Because we can only see a couple of them. I don't know where the nearest one that we can see is. I think Monoceros, the most recent one, the unicorn, it's, I don't remember how many light years. So I know the name of it for you to look up later. It is called the Unicorn. It's in the Monoceros constellation. It's about 3 solar masses. And I think this is one of the closest ones we found. I don't remember exactly how close it is, but it's, I think, the closest that we have seen so far. It's a nice small one hanging out with another star. And we were looking at the color of that star, seeing how it changed as it was orbiting around. And we're like, oh, there's a black hole there. Cool. For the distributions of other black holes, we have, there's 2 parts to that. There's the supermassive black holes and there's the stellar black holes. So for the stellar black holes, there are, I'm trying to think, millions, ballpark, within our galaxy. And then there's 1 supermassive black hole in our galaxy. But then of the like hundreds of billions, again, billion with a B, hundreds of billions of other galaxies, most of them have a supermassive black hole at their center, and they have stellar black holes throughout. So there are a lot of black holes. It's bigger than a trillion. I can't do all of that math right now off the top of my head, but it's a lot. If each galaxy has a supermassive approximately, and many millions of stellar black holes, that's a lot.
That's quite a lot. Wow.
Sometimes just the word lot is actually the most accurate you can come up with at the time.
Exactly. Could you tell us more about how the mass of a black hole is determined?
Yeah, like how we figure it out.
Mm-hmm.
So when, for example, we are looking at the black hole and its star friend, and they're orbiting around each other, we can look at the color spectrum of the star. And there's this thing called Doppler shifting, where when a signal moves towards you, think of this like with an ambulance siren. As the ambulance moves towards you, the pitch goes up. And then as it passes you and goes away from you, the pitch goes down. And it's this, the ambulance is emitting the same signal the whole time, but the sound appears to go up in pitch and then goes down in pitch. This is called the Doppler shift. It happens for sound and it happens for light. And so with light, this Doppler shift means that it can get kind of blue and then kind of red. So kind of blue is when it's coming towards you, and kind of red is when it's going away from you. We sometimes also call this blue shift and red shift. You might have heard those terms before. So as the star is orbiting around with the black hole, we can look at all of the colors it's emitting. We call this its spectrum. And we can look at it over time, as it's orbiting, and see how this changes. And these orbits tend to be pretty short. They can be down to hours, or they can be as many as days or weeks or something. So taking multiple spectra, we can look at how it changes and see the blue shift and the red shift. By doing a bit of math with how much the blue shift and red shift is happening, this tells us roughly what the mass of the black hole would be, because we can have the mass of the star. So that's how we can find that for the black holes that are eating their star friends. For the black holes that are with gravitational waves, we have to use our fancy many computer models that we run. As though I'm part of this, the many computer models that we as the scientific community run. Because all we get is that wiggle in all of our different detectors. we have to run these different computer simulations to say which combinations of masses would give us this wiggle and which fits best. And by looking at this, it's by fitting all these different models. So these predictions of what it would look like, we compare that with reality, and whichever fits best with reality, we say this is probably what it is. And this is how confident we are in that. And so that can tell us how massive we think those black holes are. For the black hole in our galaxy, Sagittarius A star, the way that we got its mass so precisely was from looking at the orbits of those stars that we looked at, those rainbow dots going around in their orbits. By looking at the velocity and time with which they were all orbiting, you can do just like high school physics math on that and figure out how massive the black hole there has to be. So that was 4.3 million times the mass of the sun. What else is there? For black holes, like super, super distant, far away black holes, we look at the light that's coming from it of like the gas that it's eating. As the gas is orbiting around, that gas can also emit a bit of blue shift and a bit of red shift as the gas is orbiting around. And so we look at that and do some math and figure it out.
That's awesome. That's awesome.
A lot of tools in our little toolbox.
And I know from a physics assignment that if you travel at a high fraction of the speed of light, red lights will appear green. So
that's true. You have to go really fast to convince the police officer of that. My car can't do that. Maybe yours can. But yeah, so the most kind of robust and reliable way that we have for doing this is by looking at the color spectrum of the star, redshift and blue shift. That we call that radial velocity, and this is considered the most reliable, robust way to get the mass of the black hole.
That is really neat. I'm excited about that. That's cool. Do black holes have a dominant electrical charge?
Black holes have no electrical charge at all. They only have a mass and a spin. So the stuff that's all around them, most of that has no electrical charge. So if you're standing far away, it appears that the whole thing has an electrical charge, but the black hole itself has no electrical charge. And this is from what we call the no-hair theorem, where there's no additional flim-flam with the black hole. There's just the mass and the spin. There's no electrical charge. There's no magnetic field. There's no anything else. Yeah.
Cool.
Yeah.
Here's a fun one. What would happen if there were two black holes beside each other? What would happen? Oh, would they eventually collide, or
they would probably smash together? Yep.
Yeah.
If they were close enough, they'd probably smash together. If not, then they would just kind of hang out, be like distant neighbors.
This is interesting. It's an interesting thought. Can a black hole be ejected from a galaxy similar to like a star?
Yes, it can. From a distance, a black hole is just kind of like a thing with gravity that interacts with other things with gravity. And so just as you can have multiple stars orbiting around, they get these chaotic orbits that are unstable. And so you can eject stars. We expect that you can also do this with black holes. The thing is, we don't really see it because we can't see the black hole. But yeah, it very probably happens.
That's very interesting to think about. Yeah. Does a black hole eventually evolve into anything, or does it just get bigger?
The black hole is the end stage. It's like the ultimate mega stage. It eventually gets bigger, and they'll eventually merge together with other ones if they get close enough. But like it is the end game.
Definitely. Does Betelgeuse have the potential to turn into a black hole when it dies?
Oh yeah, so Betelgeuse is a red giant star, or red supergiant star, that we can see in the Orion constellation. I don't recall the exact mass of Betelgeuse. For a star to be big enough to turn into a black hole, it has to be more than 20 times as massive as our sun, which is quite big. So I don't recall Betelgeuse's exact mass, but if it's less than 20, if it's like, I don't know, like 8 or so to 20 times the mass of our sun, it'll end up as a neutron star, which is also super cool. I would also be excited to see that.
That's awesome.
Yeah. But yeah, Betelgeuse you can see with the naked eye. If you just find Orion's belt, look up and you'll see Betelgeuse.
Yeah. Oh yeah, for sure. I remember a couple of years ago, there was like a panic because it was
when it was dimming.
Yeah. Everybody thought it was going to
go supernova, but there was just dust in the way. It just a bit of dust got in the way, and it was quite a bit of dust, but like We got very excited and got very ahead of ourselves and worked ourselves into quite a tizzy, and it was dust.
Yeah, that happens a lot with astronomy for sure.
Yep.
How do you undistort gravitationally lensed galaxies? Is that possible?
It is possible with a computer, yeah. So if you, by looking at the picture that you actually have, you can use the physics of how black holes bend light. You can use computer programs you often have to write yourself, or use them that a colleague lovingly wrote for you. And you can figure out how the photons the particles of light would have traveled from around the black hole. You can use that to recreate the mass of the black hole. And in doing so, you often end up recreating roughly what the image originally would be. However, oftentimes we're not actually interested in the images that are produced. They're very pretty and we like them very much. But oftentimes we're interested specifically in just all the colors of light, which you can get. The colors are still, they get bent, but like you still get all the colors. So you can correct the colors of the light, but we don't necessarily always reproduce the image itself.
Oh, interesting. What more advanced X-ray telescopes can we look forward to in the next decade or so? And what might they tell us about black holes that we can't now already learn?
Yeah, so there are a couple X-ray telescopes to look forward to. There is one that launched very recently in like around Christmas time or just after or just before, around JWST, but it was eclipsed by JWST. It's called IXPE, IXPE, and it is looking at X-ray polarimetry. So light has, again, not just color and brightness, but it also has this polarimetry aspect to it. And we have not seen X-ray polarimetry information since like the 1970s when we were using sounding rockets to get detectors up. Because again, you have to get above the atmosphere to see X-rays. And polarimetry requires an entirely different detector than one that looks at light, color, and brightness. We need a special extra detector to detect the polarimetry of this, the polarization of this light. So IXPE has some data that they've taken of a supernova remnant, and as they take more and more data and get some press releases out and get like analyze that data, because of course just taking the data is merely the first step of the whole thing. You then have to analyze it and triple check all of that and then put your paper together, and then you can get some cool press releases. So taking a look at what IXPE is coming out, that's a NASA mission centered at Marshall, I believe. That is really cool. I would definitely keep an eye on that. It's like the quiet underdog, but I think it's going to be super, super cool. Looking forward, I would love to see another X-ray polarimeter come up, a bigger one, so we can get more light. IXPE is a bit, I mean, it's very cool and it can look at polarization, which nothing else has been able to do, but you often have to have a bigger physical detector in order to get more light to see fainter things or to get more detail on things. So a bigger polarimeter would be awesome. In the Decadal Survey, so in the US for NASA, we have what's called a Decadal Survey, where the US astronomy community, which is just people working in the US, you don't have to be American, you come together and we decide as a community what our priorities are for the next decade. And then we give this to the National Science Foundation and to NASA and to the US Department of Energy to have them fund what we find most important. And so all of the massive missions that have come through have been all recommended primarily by the Decadal Survey. So the Hubble Space Telescope, the Chandra Space X-ray Observatory, JWST came through, and it was primarily recommended in the 2000s Decadal Survey. So we just had the Decadal Survey come out last year. It's a huge undertaking by the committee. And they recommended two different things for X-ray astronomy. Their primary interest was in getting JWST up and launched, because it was not launched at the time that this report came out. And they're interested also in like exoplanets, which we best look at with optical and with visible and infrared light. The two priorities that they gave for X-ray astronomy One of them would be a Chandra successor, because as I said, Chandra was launched in 1999. So it is quite old at this point and it's doing good, but like it's important to not wait until it dies to then begin to plan for its successor, since it takes 20 years or so to get something up after that. So one of the possibilities to be a Chandra successor is called Lynx, Lynx, just like the animal. And Lynx would be, a bigger, better, faster, stronger Chandra effectively. It would be great. It would be a big X-ray telescope to look at very faint things in very good spatial detail. So it would take beautiful X-ray images. There's also a call for what's called a probe. So these medium class missions, Strobex, the one I mentioned before, is one of the possibilities for a probe. There's a couple others in the running as well. And so like Strobex doesn't take images. It will just collect all of the light in like a giant light bucket. So it won't take images, but we'll see the colors of the light very, very well, which for science, we're very interested in. So those are kind of what's up on the horizon. But again, these wouldn't be launched until the 2030s.
Right, of course.
Lynx might be like 2040.
Wow. I think we should finish it off with just kind of a fun topic that a few people have brought up, and then we'll close it off. But
yeah,
would you like to comment on wormholes?
Oh, yes. So wormholes are this idea that you could kind of connect like the back end of two black holes and use them to traverse space and time. It's a cool idea. I want to preface all of this by saying it's a very cool idea. Like I love science fiction, absolutely love it, reading it, watching it, you name it. And wormholes feature prominently, and I don't mind. I enjoy it. There are very few scientific papers about wormholes, and all of them are just about the mathematics of how it might work. And all of them start with, suppose you found a wormhole. How would it work? So looking at the physics side of astronomy, the formation of a wormhole is not something that we can produce, is not something that we see as possible. So yeah, we will call this the formation mechanism. Like how would you make a wormhole? This is not something that appears to be possible given what we know about the universe. And we know a lot. Like we haven't seen all of it, but we can predict a lot of it with math, and like we know a lot. Like we're good at math. So it's a cool idea, and I love them in science fiction, but they are not astrophysical, if that makes sense. I'm sorry, but I love them in science fiction. Don't get me wrong.
Yeah, me too. No, that's great. Well, that brings us to the end of our Q&A, and I would like to thank you so very much for being here this evening with an excellent talk. And you're
very welcome. It was a pleasure to talk with you all.
You plowed through almost 35 questions, and that's the most.
Wow, we did good.
Done. Fabulous job on behalf of the Royal Astronomical Society of Canada, Calgary Centre. I offer our greatest appreciation, and speaking on behalf of everyone here tonight, I've seen nothing but positive comments coming in on the chat, on my phones, and everything. So
fantastic.
Thank you so very much. It was very fascinating.
Welcome. People can feel free to tweet at me or find me on TikTok. I'm Lipstick Astronomer on TikTok. Email, I get a lot of emails, so maybe stick to social media. But I can answer more questions there if you would like.